In this lesson, we are going to focus on artificial transmutation, nuclear reactions that are done with the assistance of humans. So let's talk about this. Artificial transmutations. Nuclear reactions are created by humans in a laboratory where we can change an element into a different element in a special laboratory called a particle accelerator. For example, the Cornell Electron Storage Ring in Ithaca, New York. This is an electron and a positron collider. What happens, we can create an element to turn into a different element. So that's artificial transmutation. Happens when a very large nucleus is hit with a particle moving at the speed of light, which causes the large nucleus to break apart and ultimately producing two new and different elements, and some additional stray particles as well. Besides academic experiments with smashing atoms, humans have created other examples of nuclear reactions that are considered artificial transmutation. For example, fission and fusion. Fission occurs when a fast, large nucleus, no, I take that back. Fission occurs when a fast neutron hits a large nucleus. Fission occurs when a fast neutron hits a large nucleus, which is then split into two smaller nuclei and several other neutrons, which can then go on to hit other nuclei. And when that happens, that's what's called a chain reaction, and that's has been done, but we also try to control that. More on that in just a minute. So fission is division. Fission occurs when a neutron hits a large nucleus. That nucleus is then split into two smaller nuclei and several neutrons as well. And again, those neutrons can go on to hit other large nuclei if there's large nuclei nearby. So how do we show that as an equation? Well, we have to start by showing a neutron. A neutron has a mass of 1 and a charge of 0. And we are going to allow that to absorb or hit or combine with uranium-235, right? And what's going to happen is that's going to turn into these two substances, barium-144 plus krypton-89 plus 3 neutrons. Now, we can figure out that the math would actually work because 235 plus 1 is 236. And if we add up 144 plus 89 plus 3 here, that's also going to add up to 236. And we notice down here, 56 plus 36 adds up to 92, and 92 plus 0 adds up to 92. So that's how that works. That's how that's justified. So where is fission used? Well, it's used in nuclear power plants. More about this in the next section. And this is also used in the atomic bombs that were used in 1945 in Hiroshima and Nagasaki. Fusion. Fusion occurs when two light nuclei combine or fuse to form a heavier nucleus. Basically, two small atoms form one larger atom. In this diagram, this is a small atom, this is a small atom. They come together and they produce this larger atom, plus a lot of energy, plus a stray neutron. So how do we show this as a reaction equation? We would start with hydrogen 3 plus hydrogen 2, turning into helium 4 plus 1 neutron. If we take a look at the top, we've got 5 is equal to 5, and we've got 2 is equal to 2. Where is fusion used or found? Well, naturally, fusion is found in stars, right? Stars use the fuel of hydrogen, and hydrogen atoms are fused together to become helium. It releases lots of energy, and we get the stars that we see today. Certain stars, the older they are, helium will fuse with other heliums, and they will fuse indefinitely until a star ultimately becomes a big ball of iron. You can learn more about that in an astronomy class. Fusion bombs, thermonuclear bombs. These were tested by both the United States and Russia. They have 700 to 1,500 times more power than a fission bomb. So they've been tested, but they've never been used as an act of warfare. Cold fusion. Cold fusion is, because this produces so much more energy than a fission reaction, and because the products are not radioactive, this is actually a very desirable source of energy, that if we could do fusion reactions to generate electricity, we could power commerce, industry, and homes with very little detriment to the environment. As of now, it has been done. We can do it. We can do cold fusion, but commercially, where we're not spending more money to do the reaction than it would take to, spending more energy in to make it happen than getting energy out, it's just not a practical form of energy production yet, but that has to be the energy of the future if and when we can figure out how to do that realistically. All right. Well, one of the things we have to talk about to figure out where all this energy comes from stems from something called mass defect. All right. So we have a hydrogen 2 atom. That just means that there's two nucleons in the nucleus. And if we were to take the mass of a proton here and that mass of that neutron here, and even if we factor in the mass of that electron, right? If we sum up the mass of those 3 particles, we get this mass, okay? But when we actually find the mass of a hydrogen 2 atom, so this is the real one, you'll notice that the actual mass is less than the sum of its parts. So some mass seems to have gone missing when we put these 3 particles together in an atomic structure. So the mass defect is the difference from the mass of the atom itself and the mass of the individual parts. That very small mass is a tiny bit less than the sum of that individual's protons, neutrons, and electrons. But that's where the energy is going to come from in these nuclear reactions. But before we talk about that, isn't that a violation of the law of conservation, right? And it is apparently so, but hold on a second. When a nucleus is formed, energy is released. This is known. And there is a reduction in total mass. This is known. This missing mass, as we said, is called the mass defect. And it accounts for the energy that is released. We can see that if we take a look at Einstein's E equals mc squared equation, where E is energy, m is the mass, and c is the speed of light, right? So imagine this, we're going to square that speed of light. That's going to give us 9 times 10 to the 16th meters squared over seconds squared. That's a phenomenally large number. So it doesn't take very much mass. When we multiply it by this very large number, that's going to result in an incredible amount of energy. The larger the mass defect, the more stable the nucleus, and the greater its nuclear binding energy. So the more mass that is apparently lost, then the resulting nucleus is going to be very stable and not radioactive. So coming back to the law of conservation of mass or energy, this applies only to physical and chemical changes, not nuclear changes. Ultimately, mass defect is the source of all nuclear energy. Bottom line, a huge amount of energy can be created by destroying a tiny amount of mass. Okay? So the answer is no. It is not a violation of the law of conservation of energy because that law only applies to physical and chemical changes. It does not apply to nuclear changes. All right, that is the end of this video on mass defect, fusion, fission as examples of artificial transmutation, which are radioactive nuclear changes that are the result of that are novel at the hands of humans. These don't happen naturally. These are all created at the hands of humans. That's it for now. We'll see you back in the classroom.